So ethane is a 2-carbon compound, so C2H6. It has a carbon-carbon bond to it. That's something that methane didn't have. Methane just had CH bonds. So ethane, C2H6, has that carbon-carbon bond. And since carbon makes how many bonds? Carbon always makes 4 bonds. If there's one carbon-carbon bond, then to make the remaining bonds on those carbons, each carbon has to be attached to 3 H's. So one carbon-carbon bond that's shared between the 2 carbons, that will leave 3 bonds remaining on each of them. So the carbon-carbon bond is formed by sigma, right? Remember that sigma bond? That's an overlap that happens directly in between 2 atoms. And in methane, right here, in methane, that was actually sigma bonding as well. Sigma. Where there are 4 bonds directly in between the carbons and each of those hydrogens. So in ethane, there's a sigma bond in between the carbon-carbon, and also sigma bonds for all the carbon hydrogens. Right? So this is how those 2 carbons sort of join together. You have 2 sp3 carbons. One of the sp3 hybrid orbitals from each of the carbons overlaps to form the sigma bond. There it is right there, between the 2 carbons. So if we take a look at the 3D structure of it, here's an ethane molecule. You'll notice the CC bond. You'll notice each of those carbons is still tetrahedrally shaped. That's because of those sp3 hybrid orbitals that were attached. So if I click my little button here, I can show those sp3 hybrid orbitals. And you can see, if you just look at one carbon, it looks like the drawing that we had before of just those sp3 hybrid orbitals in that tetrahedral shape. But now I have 2 of them that are overlapping to make the CC bond. To have the CH bonds, the sp3 hybrid orbitals from the carbon are just overlapping with the hydrogen's simple 1s orbital. That's it. There's no hybridization that has to happen in hydrogen because it just has that one orbital that can just overlap. That's all that it needs to do. Right? So it turns out that chains of carbons will tend to form zigzag shapes because of those tetrahedral angles of those sp3 hybrid orbitals. You'll notice in this little picture of hexane here, each of these carbons is tetrahedral, right? Because the hydrogens are going front and back, front and back, front and back. And in order to keep up that tetrahedral shape, the carbon-carbon bonds end up forming those zigzags. So it'll be very common for us to draw chains of carbons as zigzags because that indicates really the actual structure of it. So I didn't mention too much about bond angles yet. Ideally, in methane, let's take a look at the structure of methane page here one more time. That bond angle, 109.5, that's called the tetrahedral bond angle. And anytime that we have an sp3 carbon, or really anything that's sp3 hybridized, because there are 4 equal hybrid orbitals, they'll space themselves about 109.5 degrees apart from each other. So when I have 4 equal bonds, it will be 109.5. Anytime we have things that are inequivalent, some will be taken up a little more space than others. That's why this one is 111.12 in ethane, but really that's fairly close to the ideal tetrahedral bond angle, but because there's a CC bond that's different from those other CH bonds. Right? This bond will actually be a little bit bigger, so it will compress those CH bond angles a little bit in the other direction. But all you need to know is if it's tetrahedral, it'll have that sp3 geometry and will tend to be 109.5 degree bond angles.